Okay, here's an attempt at differential calculus in 5 minutes. Now, there's two types of rates of change. Calculus is all about gradients of graph and rates of change. The first one is an average rate of change, as we can see here. Now, an average rate of change isn't really calculus, and hopefully it's one of the easiest things you actually do in VCE maths. An average rate of change just says, where did I start, where did I finish, what's the average rate of getting there? Think of driving from Melbourne to Sydney. All you care about is how far is it, how long did it take me, and that you can work out the average. You don't care what speed you were going at any point in time, you just want to know the distance. Same concept on a graph. We're finding the average rate of change from when x equals 1 to x equals 3, then the first thing we want to say is, well, what are the y values when x is 1? So when x is 1, sub it in, and we get y equals 5 in this equation. When x is 3, you sub it in, and you'll get y equals, I think it comes out to be 27. So let's think of those 2 points. And then if you're trying to find the average rate of change between the two, then it's just saying, well, it's the gradient of that line, isn't it? It's the using the y2 minus y1 things. So we're going to do the average rate of change is y2 minus y1 on x2 minus x1, which is going to give us, what's that, 22 over 2, and that's 11, I hope. Okay, so that's average rate of change. That isn't really calculus, but whenever you see average, whenever you're being told 2 points and define the average between them, that's all you're doing. Start point, end point, find the average gradient. Okay, now calculus is really all about instantaneous rates of change. So going back to the car example, when you're driving from Melbourne to Sydney, it's saying when you passed through some sort of country town, what was your instantaneous rate of change at that point in time? And you go, well, I look at the speedo, that'd tell me. It doesn't depend on any other points. It's just saying at that instant, what speed are you doing? So it's the same concept on the graph here. You're saying, what's the instantaneous rate of change when x equals 1? So this comes into the whole idea of tangents. And you're saying, well, when x equals 1, my instantaneous rate of change is the gradient of this pink line here, which is my tangent, where it just touches the curve at 1. And you can draw tangents anywhere you want on this graph. The tangent really is, if you're thinking about drawing your pen along the graph, it's what direction is your pen going at that point in time. Usually the tangent, like a tangent here, you'll find that the black curve just on either side of the tangent is on the same side of the curve. That's on 99% of the time. The tangent's going to do that. So there's the tangent there. The tangent up here is like a straight line. There is one exception. A tangent at a point of inflection will be, say, round about here. That's when the curve goes from curling up. The curve goes from curling up to when the curve starts sort of curling down. You get a point of inflection. At that point in time, the tangent will cross the graph. But I think you get the idea there of how to draw a tangent. So the first method then of finding the derivative using this tangent thing is to draw one, so like this one we drew here at 1, 5, and then you get a bit of graph paper and you'd say, oh, let's try and find another point on this tangent. Let's say I picked this point round about here and said that was 3, let's just estimate off our graph paper. Let's pretend we had that and we said it was approximately 3, 24. Then maybe an estimated instantaneous rate of change would just be to do y2 minus y1 on x2 minus x1. Whoops, that's not right. X1's that, isn't it? And that would be about 9.5 if we work that out. It's not a very good estimate because we're only just guessing off graph paper, but it's not a bad start. A slightly better method, given we've got an equation, because we have an equation for this, we could say, well, one estimate could be that rate of change that we estimated before. Let's use blue here, and say, well, that line we had before is sort of the gradient of the blue line is sort of an estimate of the gradient of the pink line, isn't it? It's a pretty bad estimate if you ask me, but it's an estimate. So we could say, well, our first estimate is that line we had before, which had a gradient of 11. Now you say, that's terrible, Mr. Rogers. Give me a better estimate than that. So we could say, well, let's find another point in here that's really close to on the graph. If we used a point 1.1, and if you sub in 1.1, you get 5.929. And you say, well, if I then tried to get the gradient between those 2 points, that sort of blue line there, you think that's actually pretty close now. That's going to be a pretty good estimate because we've picked a value of x which is really, really close to the initial value. And so then a better estimate is going to be 5.929 y2 minus y1 on 1.1 minus 1, which will get us, I think, about 9.29. So that's a much better estimate than 11 because our 2 points are really, really close together. So that's another way you can go about things. Find 2 points that are very close, and that'll give you a pretty good using the average rate of change to give you an estimate of the instantaneous rate of change. Now, what's another method? Another method then is to use first principles differentiation or calculus. And you say, well, if again I use this gradient or this average rate of change concept, then if I use x plus h as my x value, I get this estimate of saying, well, the y2 minus y1, y2 is f of x plus h, y1 is f of x, x2 is x plus h, and x1 is x. So when you say x plus h minus x, you're just going to get h on the bottom. And then I say, if I let h become really, 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 really small, then this estimate's going to become extremely good. And the way we say that is we say the limit as h approaches 0. As h becomes really small, that's a really good estimate of, in fact, it becomes the exact derivative of this thing. I won't go into how to do that in detail here, it's a whole video of its own right, but that's the concept of limits. And then finally, the way you're going to use 99% of the time, when you know how to do it, is we say, well, we can use calculus, we can use the rule to determine the gradient of this curve instead. So we can say either dy dx, that's one notation, or f dash of x is another notation. They're all a way of finding the gradient. And the rule for this curve, once you know it, is you drop the power down the front, the power comes down the front, minus 3, and you lose 1 off the power, minus 3x squared, plus, again, the 2 drops down the front and joins its friend, the 6, and you get 12x. And then that would tell us for any x value, if we just sub the x value into there, it tells us the gradient. So when x is 1, so the derivative when x is 1, f dash of 1, is equal to minus 3 times 1 squared plus 12 times 1, which gives us 9. So as you can see, those estimates were getting pretty good a couple of methods ago. The exact answer is actually 9. Hope that's helpful.